Okay, good evening, everyone. Thank you very much for coming here. Well, it gives me a great pleasure to introduce Robert Barro, the Economica Phillips Lecturer this year. The purpose of the Economica Phillips Lectures is to commemorate the contributions of Bill Phillips to economics, and in particular his famous Phillips curve, which was published in Economica in 1958, where Robert Barro, along with Robert Lucas, who was the first Phillips lecturer, has been instrumental in destroying the Phillips curve and what it stands for. But as you know, we love criticism here at LSE. Now, Robert was educated in physics at Caltech, and if Wikipedia is to be believed, as my source of all information these days, he switched to economics because he found physics too difficult. He switched in style, however, getting a second PhD after his physics one in economics from Harvard, where he's now the Paul Warburg Professor of Economics. Now, since then, Robert has done so much influential work in different areas of research in economics, changed his style every time, that if he was in fine art, he would have rivaled Pablo Picasso in style changes and influence. But in economics, I believe he has no rival with his many papers, influential papers. Now, like many of us, however, Robert started life as a Keynesian. You may not believe that, but I've actually read his Keynesian papers, working with the late Herschel Grossman on an influential book on fixed price economics, and that was around 1970. His second influential piece of work, which was published in 1974, is arguably still his most influential, and it rebranded Robert as a Ricardian. He established a proposition that I suspect most of you students in the audience had to prove at some point in some exam paper. The proposition is that under certain conditions, financing fiscal spending with debt or taxes makes no difference to their economic impact. But I guess Mr. Schäuble and Mrs. Merkel are not great fans of this theory, but give credit to my Greek compatriots for putting it into practice, refusing to pay taxes and financing all their spending with debt. If it makes no difference, why not? But that was to their detriment.
I'm responsible for that?
Yeah. They're grateful to you. But then came rational expectations and the impact, well, I guess that was rational expectations as well, and the impact of monetary policy, which was the final nail on the coffin of the Phillips curve, I guess, and that established Robert as one of the key founders of the new classical school. After that came a lesser-known paper that nonetheless killed the fixed wage model as a foundation of aggregate demand effects in the labor market. One criticism that I'm pleased to say does not apply to the search and matching model of the labor market. True? There followed the famous Barro-Gordon inflation bias model, another favorite of examiners, and so on and so forth. But you probably heard enough of me. I give the floor to Robert to tell you the latest fascinating work that he's doing on big events. Thank you. Robert Barro.
Well, with respect to physics, what's true is that I have a bachelor's degree in physics from Caltech. I took the lectures from Richard Feynman at that point. It's actually the only time he lectured to the undergraduates. Freshman, sophomore year, I happened to be there, and then his famous lectures came from that time period. I don't think I thought that physics was necessarily harder than economics, but I did become convinced that I wasn't going to be a great theoretical physicist. And the thing with Feynman is that you learned right away what it would be to do actual research in physics. And it was good for me that that happened quickly by the time I was a freshman and a sophomore, rather than having to wait until later to figure out I shouldn't be in that field. So it's a great pleasure to be giving the Phillips lecture here. When I was a kid, I was a fan of the Phillips curve. I guess as I evolved, I became less of a fan, and still think it was an important contribution, of course. Now, it is true that one of my colleagues who gave the Coase lecture here some time ago told me, well, you know, Coase was really a better economist than Phillips, and therefore it's really more important to give the Coase lecture than to give the Phillips one. And I'm not sure about that. I mean, my main approach to thinking about what's important or not is to use a market test. So I would look at how much, for example, there were citations to these different articles, and I frankly have not checked which one was cited more. Of course, these are two of the most cited articles ever in economics, and it's not completely fair because people often say Phillips curve and they don't specifically cite the original article, so it's a little complicated. So I'm happy to be giving the Phillips lecture despite what my colleague said about it. What am I using to change the...
Pull out that drawer.
Oh, I pull it out. That's what it is. Okay, thank you. So I've been working for some time on this area about rare macroeconomic events, particularly motivated by trying to explain some regularities associated with financial markets, asset pricing, notably the equity premium puzzle. And I've tried to argue that the low probability chance of very severe downturns can be used to explain certain features of asset pricing, especially why the average return on equity is much above the risk-free rate. So I'm going to try to argue today that I can use the perspective from that analysis, which arguably had some success, to think about a different problem, a problem related to environmental protection. So I'm going to think about the issues here as particularly having to do with low probability but potentially very serious consequential large events. So I'm going to think about fat tail risk, which I'd explored in this macroeconomic finance context as applying to this other area. And as I've been thinking about this recently, I think maybe this application actually suits the framework better than the original one that I had considered, and that's what I try to make the case for that today. So of course I'm not really an environmental economist, and I hadn't really thought a lot about environmental issues, and I'm trying to think from a basic conceptual perspective about how to think about aspects of how much would you invest, for example, in mitigation of environmental risks. And certainly one thing I was influenced in that regard was by the Stern Review, which came out in 2007. By the way, I've been trying to converse with Nick Stern on these issues, and I've tried to talk to him about this work over the last numerous months, and I finally, just a couple days ago, got a really substantive email from him. I know he's very busy. I think he actually read the paper finally, and he actually gave me some very useful insights, which I haven't had the time to work on yet. But he seems now to be more amenable to the way I'm thinking about this problem, maybe because I think it really is true that the kind of approach I'm taking can strengthen some of the arguments that are in the Stern Review rather than criticizing them, which of course has been very common in the economics literature since the 2007 review. It's kind of well known that discount rates play a central role in thinking about the analysis in the Stern Review. Basic idea is that if you have a very low discount rate, something fairly close to zero, then as long as the flow of benefits exceeds the flow of costs, you can more or less justify almost anything, and you get a pretty high net present value then if you use a low enough discount rate. And a lot of the argument in the review is that it's somehow reasonable to be using a discount rate of, say, 1% a year or something in that neighborhood, even though rates of return on private capital tend to average something much higher, like 5, 6, 8% per year. And many economists have criticized the review on this ground, that it's not really appropriate to be using these extremely low discount rates. Now, it's also true that the review has a lot of stress about uncertainty. And the general message, particularly from the introduction in the review, is that because there's uncertainty about what the consequences could be of, for example, not doing anything to mitigate environmental disaster risk, that strengthens the case for doing something, the fact that there's a lot of uncertainty. Now, I think that argument is in some respects quite correct, but the analysis in the review is really problematic here because it basically does not have a serious treatment of uncertainty. The underlying model that's used to get results is deterministic, and you can't really then think about uncertainty, and you can't even think about what appropriate discount rates are in an environment that doesn't seriously model uncertainty. Another problem in thinking about uncertainty is there are really two kinds of uncertainty that come into play in the analysis that I want to consider. One is that there's a chance, maybe a low probability chance, of a very large set of damages. That would be the tail risk problem. And the fact that that's the characterization of uncertainty, I think, does strengthen the case for doing something. And that's particularly true if people have a substantial amount of risk aversion. But these are things you can't really consider within the model that's in the review. And it's also the case that there's a second type of uncertainty which is important that goes in the opposite direction. Another kind of uncertainty that's significant is that a lot of things you might be doing in the way of policy intervention, there's a lot of uncertainty about what the impact is going to be. The policy effectiveness is subject to a great deal of uncertainty. Now, that tends to work in the opposite direction. That tends to lessen the case for doing a lot of intervention if you're not really sure about what the impact is going to be of the kind of investment and intervention that you're undertaking. So my colleague Marty Weitzman, I think, has had a number of interesting reactions to the Stern Review and the related literature. I think his big argument here is that you don't want to think about the investment in environmental mitigation as having particularly to do with doing something now versus doing something later. He tries to argue that the main thing you want to think about is how can you invest to reduce the probability or potential size of these disaster events. So then there are two key relationships that will come into the model within that Weitzman perspective. The first is how much is it worth to society to reduce the probability of an environmental disaster, something that starts out with a fairly low probability, but maybe you can make it even lower. The question is, how much is that worth? And the second thing is, how much does your intervention actually help in that regard? How much does it actually reduce the probability of disasters? And I should say that when I'm talking about probability of disasters, you can think more or less interchangeably about lowering the potential sizes of disaster events. Those work more or less in the same way, at least in the framework that I'm considering. So I'm going to try to get some insights in thinking about this environmental problem from the work I've done on rare macroeconomic disasters. So let me try to say something about how I'm going to use that set of results. So I'm going to jump ahead a bit. This is going to be a quick summary of the work I've been doing since 2006 about rare macroeconomic disasters. And then I'm going to try to use some of the insights I get from this work, both the conceptual model and also the empirical results, to try to inform something about the environmental protection problem that I'm going to be considering. The baseline model has something like GDP and consumption evolving in accordance with certain shocks. So that's what's in this equation 1. So here GDP would be indicated by the symbol Y, but this will also be consumption, as is true in the simple Lucas tree model that I'm using as a baseline framework. So this is just something about thinking of the growth of GDP and correspondingly the growth rate of consumption in this simple framework. So there are three things that enter into thinking about the evolution of GDP and consumption here. One is that there's some normal growth rate G, which I don't do very much with in the baseline framework. Second thing, there's some kind of shock U, which is going to look like some kind of business cycle disturbance. And as in the Mirror and Prescott famous article that introduced the term equity premium puzzle, that's not going to play a central role in the analysis. It's going to be too weak quantitatively to matter a lot. What is going to count is this disaster shock, which is denoted by this term V. So in the macro context, I thought about low probability events characterized by some probability P per unit of time, which when they occur generate a sharp contraction of GDP and consumption. And the parameter B represents the size of the contraction. So if B is 0.2, it means that you're losing 20% of your GDP and consumption. And in general, there's going to be some distribution over those sizes that occur, and I'll show you what that looks like in the macroeconomic context. So I'm going to be trying to use some of the results I got from the macro finance side, particularly with regard to probability and size of disasters, to inform myself with regard to the environmental problems where it's more difficult, I think, to observe things directly. This histogram summarizes what I found for the history of macroeconomic disasters. Now, this is coming from a data set for countries where you can get data on GDP going back at least from before 1913, and in many cases as far back as 1870. It turns out to be, this is a sample of 40 countries where you can get this long-term national accounts information. It includes the rich countries, but it includes a fair representation also of developing countries. For example, Cyprus is in this data set. So it must be serious. So these are annual data, about 40 countries, over a century of data each. It turns out to be almost 5,000 annual observations. So the nature of this data set is it has enough data points so that even if you have disasters being rare events, you get a fair number of realizations within this sample. So I'm going to take this kind of rational expectations approach that I'm going to gauge the probability and sizes of disasters from what one actually saw in the data. So then my measure of probability of disaster is going to be kind of a rational expectation of what that is, at least given the history. That's the approach that's going to be taken here. So it turns out, I should say that this data set owes a lot to the work by Jose Ursua, who was formerly my student at Harvard. But unfortunately, Jose took a job at Goldman Sachs, and that means he's not as available for doing research as he used to be. But Jose did a lot of work in terms of constructing the underlying data on GDP and consumption that we used in various of our studies. I should say, I won't go into this in detail. We started with the Angus-Madison data on GDP, which are frequently used. And we thought that we could use that as a basis and then extend that to try to measure consumption, which is more like what appears in the usual asset pricing formulas, because we wanted to think about the classical asset pricing puzzles such as the equity premium. And for that, we needed data on something closer to consumption rather than GDP. So we started on the data project with the idea that we could use Madison and extend on that, since he only had GDP, to measure consumption. Then it turned out Jose looked more closely at the Madison numbers, and it's kind of a horror show when you look too closely at what the numbers are. And there were many cases with a lot of problems, so that meant that Jose ended up spending a lot of time reconstructing all the GDP data and not just the consumption data. But I'm not going to get into that in more detail unless people ask me something specific. So the results in this histogram are for the data on gross domestic product, real per capita, and not per se on consumption, but we have that underlying information as well. The histogram just deals with the cases where in a peak to trough sense, the declines in per capita GDP were by 10% or more, which is quite a large contraction, larger than almost all the cases, for example, that you saw in the recent Great Recession. Among these 40 countries, the only 10% declines that you saw in this recent period were for Greece and Iceland. So there were a couple realizations there, but most of the events depicted in this diagram are bigger than the recent Great Recession. It turned out there were 185 realizations of these disasters as defined, and the average size conditional on being at least 10% was 21%. And this shows you what the form of the distribution looks like. And it marks out particularly the largest of these macro declines. The biggest is Germany at the end of World War II, where it's a decline by around 70% in per capita GDP over around just 2 years. And you can see some of the other events that come in. A lot of these are associated with wartime. A lot are associated with Great Depression type events, usually related to financial crises. And the only other set of results that we found in terms of where were the 10% declines, we think are from the great influenza epidemic of 1918 to 1920. And there seemed to be 8 or 10 countries that had declines there that we thought could be attributed to that particular disturbance. We didn't find other kind of natural disaster events that showed up as at least 10% decreases in GDP, things like tsunamis, hurricanes. For this sample of 40 countries, none of these were big enough to show up at the country level in terms of declines over the relevant time frame. So that's a kind of limitation, but I think that's what the history is. It's also true that there are no environmental disasters as usually considered in this sample, which is a limitation in terms of thinking about the analysis. I'm thinking about disaster probability P, so that's per unit of time. And in the history that I used for the macro declines, that turned out to be about 4% per year. So on average, a typical country sees a disaster occur with a probability of 4% in terms of getting into a disaster state, which means that it occurs roughly every 25 years. That was an average over the countries and time periods. So now I want to think about the disaster probability P as being composed by 2 components. One is this pi is these non-environmental disasters, which I think I've seen in the data. That's what the histogram referred to. And for the environmental application, what will be crucial is the probability of those kinds of disasters. I call that Q per year, but I don't know how to calibrate exactly what Q is from the data because there were no realizations of this sort, of what I'm thinking about as an environmental disaster. Anyway, the total disaster probability per year is the sum of these 2 types. So one assumption I'm going to make is that the potential sizes of the disasters, which is governed by the distribution of this thing I called B and was in the histogram, I'm assuming that's the same for environmental and non-environmental disasters. So I don't see any environmental disasters. I've got a lot of information about the non-environmental ones, which look like wars and financial crises and the great influenza epidemic. So I'm going to assume the potential size distribution is the same. Now, there actually is a part in the Stern review where they make that kind of a jump. And in making their assumptions about how big environmental catastrophes might be, they say, well, maybe this is as big as the history of what we've seen with regard to the worst war-related and depression-related events. So that's the kind of comparison I'm making here. I'm assuming I can do that, but it might not be correct. But that's how I'm going to pin down something about the potential size distribution of these events. It's going to be central in this analysis to distinguish risk aversion, an important aspect of consumer preferences, from willingness to substitute consumption over time, which has to do centrally with saving behavior. So in order to make that distinction, I use a form of utility that was pioneered over 20 years ago now by Epstein and Zinn. So I'm using a form of utility function which allows me to distinguish these 2 key aspects of preferences. The most standard form of preferences that's used mixes together these 2 parameters, and that's going to be a real problem with regard to this application. It's a problem with regard to thinking about returns on equity, and it's also a problem with regard to this environmental application. I'm going to think about the coefficient of relative risk aversion, which is going to be central to the analysis, to take on a value that was estimated from the results about the macro disasters. So if you wanted to explain the equity premium, given the probability and size of macro disasters as was estimated from the disaster data, it turned out you needed a coefficient of relative risk aversion in the neighborhood of 3 to 4, which is substantial but not astronomical. In contrast, in the original paper by Mirror and Prescott, they pointed out that with just the normal fluctuations, you needed a coefficient of relative risk aversion of around 100 to get into the right ballpark. And I guess if you have that kind of attitude toward risk, you never get out of bed in the morning. So that seemed to be a little problematic. And they didn't just regarded this as a failure. They just said that this model doesn't work. It doesn't fit the facts about, for example, the equity premium. So the disaster risk changes that perspective. And I think now you can use a risk aversion coefficient that's kind of plausible. So that's what I'm going to assume in the application to the environmental problem. The attitude toward consuming over time is less important, but I'm going to assume that the coefficient there gives you an intertemporal elasticity of substitution which is greater than 1. That makes some of the properties sort of more sensible, but that is much less central to the results than the attitude toward risk. It's the risk aversion that's really critical in this problem. Okay, I have a very stylized way here about thinking about environmental catastrophes and about what you might do to mitigate those. I think it's very easy to complicate this model, and in particular to bring in a much richer set of dynamics, but I don't think that's going to change the basic trade-off and kind of at least rough quantitative balance in terms of the results, but that's yet to be demonstrated. So the way I bring in this analysis is the following. I assume that at any point in time, society chooses to devote some fraction of its GDP to mitigating environmental disaster risk, some kind of investment, and I call that ratio tau. So tau is a ratio to GDP. It might be that you give up using some forms of energy that are heavily polluting, even though that costs you something in GDP at the time. That's the kind of thing I have in mind. So there's some ratio of investment to GDP. Generally, you would think of a whole time path of those investments. But the model I construct is simple enough that the investment ratio that's optimal turns out to be constant. And there's various features of the model that deliver that, and it's quite easy to enrich the model so that it's no longer true that the optimal investment ratio is a constant. But I'm not sure that that's going to change the basic insight. So I'm sticking here with this basic framework. Now, the idea is if you invest more, that's going to reduce either the probability of these environmental disasters, which I call Q, or the potential size of disasters, and those work in a similar way. Here I'm thinking about reducing the probability Q, and I have a particular functional form here with this negative exponential. And the critical thing in this functional form is there's a parameter lambda which governs how effective the policy is. So a larger lambda means that this probability is more responsive in a negative direction to your interventions. So this policy effectiveness parameter is going to be central. So there are two things that are going to matter for the results that I have a tough time pinning down. One is the parameter lambda. The other is the baseline probability of environmental disasters, which I didn't know how to pin down because I don't see those in the data. So those two things, the kind of Q of 0, what is the baseline environmental disaster probability if you're not intervening, and how much you reduce that probability by investing, which is governed by lambda, those are the two things that are going to be central to the results, and that I don't think I have too much information about. Let me describe within this framework what is the answer in terms of optimal investment, and then I want to relate that back to these issues about discount rates that I talked a bit about at the beginning, because this is going to have implications for that. First off, in this model, it's relatively easy to price various asset claims, including claims on equity, which look like ownership rights in these Lucas trees. So these are trees that spit out fruit at every point in time, and you can think about pricing those ownership rights, and I call V the price of one of these things. So you can think about it as a price-dividend ratio, where the dividend is the consumption that comes off the tree in the form of apples that fall off the tree or whatever, fruit. The equation here is the reciprocal of that. So that's going to be a dividend price ratio, which is going to look like a rate of return associated with these Lucas trees. And you can show in this model what the formula is for that dividend price ratio, and I'm not going to try to derive this, but it has some results that make sense. And the most important part of this set of results is that the disaster probability P and the size distribution of disasters, which is governed by this B, those are going to be very important in thinking about this pricing. That's where the rare disaster stuff comes in the previous work. So that's going to be part of this formula, and I'm going to apply this to the environmental context. You can also write, this is a very straightforward formula here, that the dividend price ratio on these claims, on these equity claims, is the difference between the expected return you get by holding one of these equity claims. So that would be like the expected return on the stock market in a simple model, less the expected growth rate. Or if you flip this around, the expected return on holding a claim on equity is the dividend yield, which is 1 over V, the dividend price ratio, plus the expected capital gain. And the expected capital gain corresponds to the expected growth rate of consumption, which is the dividend. And that's this G star thing. That's G star is the expected growth rate of consumption and GDP in this model. So this is just saying that the expected return on these equity claims is, as usual, the sum of a dividend yield plus the expected capital gain. So that's going to be part of this model. This framework is simple enough that you can write down a simple formula for what the utility is that's attained by the representative household in the model. This has been worked out in previous applications of this Epstein and Zinn framework, so it's not original. But the important thing about this equation 11 is that you can write the utility that's attained by the representative household in terms of this asset price, V. That's the price-earnings ratio of the claims on these Lucas trees, which are these perpetual streams of consumption. And it also depends here on how much of the GDP goes to environmental investment, which is the tau, and it depends on the current level of the GDP. So in particular, you get some results that seem natural under some conditions, at least. If you hold fixed the asset price, which is the V, then a higher environmental investment ratio, tau, decreases utility because less of GDP is going to consumption, and consumption is what you care about. But on the other hand, higher tau is supposed to reduce the disaster probability or disaster sizes, and that's going to end up in this basic framework raising the price of equity, and that's in turn going to be transmitted to utility. So that's going to work through the V in this formula. And then a higher level of GDP today is going to be associated with higher utility. That's not surprising. That's the last term on the right-hand side. So this is a very simple way of capturing what determines utility. And in this model, then, the choice of optimal environmental investment, which is the ratio tau, is going to be straightforward. You're going to pick tau to maximize this utility. And in the way the model is set up, the answer to that is going to be a constant. It's going to be the same at every point in time, although a richer model would have a more complicated dynamics. I want to just talk about this first order condition that emerges from this, because I think it has some intuitive appeal, and it relates to the issues in the Stern review about what discount rate is appropriate. So if you work out what is the optimal environmental investment ratio, tau, it's going to be the one that satisfies this first order condition. So one important thing about this formula is that the thing on the left is a discount rate associated with the expected return on equity. Now that's going to be a high discount rate. And in fact, this model supposedly is explaining the equity premium. So it's going to be quite a high rate of return. So an average value of the expected return on equity might be something like 6, 7, 8% per year. And then you subtract an expected growth rate, maybe 2%. that's going to give you the discount rate that matters in terms of thinking about an optimal investment. It's going to be a high discount rate. Now, the reason for that is I followed the standard practice of modeling an environmental disaster as a decrease in GDP and consumption. Environmental disasters were like other macro disasters, and when they were realized, GDP and consumption declined. So the impact of that assumption is that environmental disasters are heavily pro-cyclical. So when there's something bad going on with the environment, GDP and consumption are low, because an environmental disaster is a decline in GDP and consumption. So that means if you're thinking about what discount rate should you use in thinking about investments that pertain to the environment, it's going to be the discount rate appropriate to something that has this strong positive covariance with consumption, like stocks. And that's why the relevant discount rate in this model, and I think much more generally actually, if you think of modeling environmental disasters as declines in GDP and consumption, it's going to be this high discount rate, something like the return on equity. But that does not mean that there's a weak case here for making environmental investments, because what environmental investments do, by assumption in this structure, is reduce either the probability or size of these events. And if you have some kind of event or investment stream that's highly risky, like something about return on private capital or equity, if you can do something to make that less risky, that really is very rewarding. That's something important. So the right-hand side of this first-order condition puts in the value of doing something that reduces the probability of these events, which are themselves events that have a high price associated with them because they have this positive covariance with consumption, that when environment is bad, everything else is bad, and therefore you put a big weight on that because you've got high marginal utility, if you like. So there are two consequences here from this way of viewing the rates of return. One is you need a high hurdle rate of return to do something. But secondly, on the right-hand side, the benefit from doing something is also magnified. And at least in terms of the numerical exercises I've done, the right-hand side effect is really what's dominant. So it turns out there's a pretty strong case in this model, depending on some parameters, from doing something that mitigates environmental risk, even though the required return is high in this model. So that's two respects in which this analysis differs from that in the Stern review. One is that the required rate of return is high, and I think more realistic. But secondly, even despite that, you can easily make a case for substantial investment in mitigating these risks. I'm just going to say a few things about some results that arise here. In order to figure out quantitatively what this model implies, I need a set of underlying parameters. So some of these come from the work that I've done on rare macro disasters, most especially this coefficient of relative risk aversion, which is pretty important quantitatively for the results. Then there's a bunch of other parameters here that I won't go into that matter more or less. Two things that are important that are not informed by my previous work are the baseline probability of environmental disaster, which I called Q of 0, and the baseline exercise I go through assume that that's 1% per year, but I don't have a direct way of informing what's a reasonable number there. And I can see how the results are sensitive to that, but I don't have the same kind of historical information to pin that down. The other thing that's important is this policy effectiveness, which I bring out in these various tables. So I'm not going to go through all these results. The first set of results pertains to the baseline parameters that I had in the table that I just showed quickly. So let me think about different values of this policy effectiveness parameter, the lambda. So if you take a lambda of 10, what a lambda of 10 means is that if you think about investing at 1% of GDP rather than 0, 1% of GDP for some reason is a focal point in the Stern Review. They want to try very hard to rationalize investing at least 1% of the GDP in environmental mitigation. If you have a lambda of 10 and you start with a disaster probability of 0.01 per year, that's the Q0. What that means is that if you shift investment from 0 to 0.01, you reduce the environmental disaster probability by 10%. That's 0.01 times the lambda, which is 10. And that means you reduce it from 0.01 to 0.009. That's what a lambda of 10 means. So it's going to be important how effective the policy is as gauged by the lambda. And I'm just telling you what a lambda of 10 means, but unfortunately I don't know whether that's a reasonable number or too high or too low. And that's why there's some missing elements in this. So what I can show in this analysis is how do the results depend on what that parameter is, how effective policy is. And secondly, I can take account of the fact that there's really a tremendous amount of uncertainty about what the true value is for this effectiveness. So I can bring in the fact, illustrated by the fact that I'm using a tremendous range for this parameter and thinking about the results. What is the consequence of that uncertainty in thinking about the answers? So for this baseline set of results, for a lambda of 10, it turns out I get an optimal investment ratio, which is a little more than 1% of GDP. And if it's more effective, you get more. And eventually, that starts going down because you've already reduced the probability so much that at the margin, the return is reduced. So you can get into the ballpark or even beyond the kind of baseline investment ratio that the Stern Review regards as reasonable with the kind of baseline parameters that I've tried to describe. Now, the results depend quite a bit on some of the other parameters. So risk aversion is central to this. And I told you what I assumed in the baseline calculations. If the risk aversion, instead of being around 3, is equal to 5, then you get much more investment being warranted, because you're trying to avoid these tail risks, which get a lot more weight when you have more risk aversion. Now, the point is, when risk aversion is higher, what happens is you get more environmental investment. At the same time, you have higher rates of return associated with the relevant discounting. So the expected return on equity, which is the relevant discount rate I was arguing for thinking about environmental investment, goes up a lot when you think about a higher risk aversion, but you also get more investment. So that's a case where higher rates of return, higher hurdle rates of return, are associated with a greater amount of investment, because the thing on the right-hand side, which is the benefit from reducing disaster probability, is also blown up, and that's the dominant effect. So that's a case where you get higher rates of return associated with more investment rather than less. Something that's similar is if you blow up the potential sizes of these disasters. So that's what's in this next panel. If you multiply the disaster sizes by, for example, making them all 10% higher, that's similar to having more risk aversion. That raises how much you're willing to invest. It's another case where the relevant rate of return rises at the same time you get more investment. The baseline environmental disaster probability is very important. So I assumed it was 1% per year, but of course in the sample I didn't see any of those realizations. If it's instead only 0.5% per year, that makes a pretty big difference, and your optimal investment is much lower in that context. So I'm not sure what a relevant probability is, but the results are pretty sensitive to what the baseline disaster probability is. In the next panel, you can consider the kind of implicit rate of return variation that's in the Stern Review. It's implicit in that analysis that the thing that's driving higher and lower discount rates is pure time preference. And they try to argue on philosophical grounds that that should be a very low discount rate because you don't want to penalize future generations. Now, it is true also in the analysis I carry out that if the pure rate of time preference is lower, that you get more investment being optimal. That's a case where lower rates of return go along with more investment. And that's the case that's highlighted in the review. It's implicit in that any time you have something that lowers the relevant rate of return, you're going to get more investment. That's true for the pure rate of time preference, but not true for the other cases that I mentioned. This business about willingness to substitute over time and consumption, that turns out to be not very important in terms of the analysis. So I have some results there that I won't try to go through. So let me go a little further. Oh, I should say as an aside that where I got the rate of time preference from, along with the risk aversion coefficient, was I was trying to use the model to explain some observed data on rates of return. So I was basically trying to explain two things. I was trying to explain levels of returns and the difference between rates of return on equity and risk-free rates. Those were two things I was trying to use the model to fit. So I'm basically fitting those two observations by specifying what the coefficient of risk aversion is and also what the pure rate of time preference is. So the parameters I used for those two objects were the ones needed to accord with the historical averages of rates of return on equity and something close to a risk-free rate. So I didn't get a rate of time preference by appealing to some kind of philosophical argument. I got it by, in this model, trying to explain the rates of return that were observed in the data. I can make an extension of this model, as I've already described, to try to think about this policy effectiveness as being uncertain rather than known. So in the first set of exercises, I specified some policy effectiveness parameter, which was this lambda, but then I pretended that everybody knew exactly what that was, and I got the optimal investment ratio. That was the procedure until now. Now, of course, it's pretty clear you have no idea what that policy parameter is. So the next extension brought that uncertainty explicitly into the analysis. So the idea here is that the parameter lambda is subject to some probability distribution, and you don't know what it is ex ante. What tends to be true is that greater uncertainty about policy effectiveness lowers the extent to which you want to do investment. This is analogous to an exercise in macro policy that was carried out long ago by Bill Brainerd in a paper from 1964, I believe it is. So he brought into the analysis the fact that, for example, a monetary authority doesn't really know how its policy intervention affects things like GDP and inflation. So he explicitly brought that uncertainty into the policy optimization problem. There hasn't been that much work done along those lines, which is kind of surprising because I thought that was an important insight. But anyway, this is an application of the Brainerd idea to the environmental investment problem, specifically bringing in the factor that you don't really know the policy effectiveness. So what that does is it tends to reduce investment. So this table just illustrates that. So if you look at the first line, I mentioned before a policy effectiveness parameter lambda of 10, and I tried to describe what that meant. So the first line is where that's the value of lambda, and you know exactly what it is. And with all the other parameters, it turns out then you want to invest 1.4% of GDP in this mitigation. So the next two lines look at what happens if instead of knowing what the parameter is, with equal probabilities half and half, you have values above and below 10. So for example, the third line, it's equally likely that the parameter is 5 or 15. So this is just bringing in a spread in the possible effectiveness without changing the mean of that value. So what happens in this particular case is that the optimal investment falls from 1.4 to 1.1% of GDP. So it's a moderate kind of impact, not enormous, but it's certainly noticeable. And it does go in a direction where I think your intuition would lead you, that you'll do less investment if you don't really know the impact of what you're doing. So that goes against the idea that uncertainty in general is going to encourage more investment. Another extension I've looked at is concerning the idea that environmental disasters are modeled in the standard way as reductions in consumption and gross domestic product. So Weitzman also has a criticism of this standard approach. Some people have criticized me for quoting Weitzman too much in this paper. As I mentioned at the outset, I'm not really an environmental economist, but I've read a number of papers now, and I guess I found Weitzman's papers most enlightening, particularly at a basic conceptual level in terms of the papers that I've looked at. Plus, Marty gets very happy when I cite him in a favorable manner, so I figure I may as well do that. Anyway, he has a quote to the effect that why is this the right way of modeling an environmental disaster? It's just a big drop in consumption and GDP. So I thought that was a reasonable criticism, although I think it's the case that standard views about what will happen if you change this perspective are, in fact, in the wrong direction. So one simple alternative is to think about consumption, ordinary consumption, and environmental amenities. Maybe it has something to do with air quality or water quality. Think about those as two different forms of goods that yield utility, and maybe they enter in a completely separable way in utility functions. And further, maybe they're completely separate in terms of how they're subject to shocks. So if there's an environmental disaster, it might not particularly correlate with either high or low consumption and GDP. That would be a possibility that's completely different from the standard one, which was the one I've used up to this point. If you model it this alternative way, and if you think about, you can think about kind of the shadow outlay on environmental amenities in this framework. And suppose it's true that that always remains relatively small as a share of total effective consumption. So suppose you have consumption, ordinary consumption, you have environmental amenities, this kind of shadow share of total consumption going to amenities, suppose that stays small and the shocks are independent. Well, in that case, the relevant discount rate associated with doing something with the environment is going to be very low, and it might be a risk-free rate. That would be a possibility. And there are some discussions in the literature that relate to this that I think are consistent with this view. But where I think the standard insight goes wrong is that the usual view is if you have a lower discount rate associated with environmental investment, it's going to mean that you're going to warrant greater investment. So I'm going to be shifting here from a discount rate that's like the rate of return on equity and capital, which is a pretty high discount rate, to one which is more like a risk-free rate, which is going to be much lower. But then the idea that that means lower environmental investment is actually completely incorrect in this model, because you're going to get a first-order condition analogous to the one I wrote down before. And the thing on the right-hand side, which is going to be the value of reducing probability or size of disasters, is also going to be much smaller. So if you have something that's completely orthogonal to ordinary consumption and isn't that big, and then you're doing something by way of intervention to reduce the probability or size of that, it's not going to be nearly as valuable. It's not going to have the same risk premium, in effect, in terms of what value do you attach to reducing the probability of that stuff, of that kind of event where something bad happens. And in fact, that effect is going to more than dominate the fact that you're using a lower discount rate on the left-hand side of the first-order condition. So what you tend to get if you shift to this alternative, which maybe makes some sense, I'm not completely sure, you're going to get a much weaker case for environmental investment than you got in the initial model. And I think that's not the standard understanding of what happens when you make this kind of a change in the framework. So it is true that you get a much lower discount rate, and it might be more like a risk-free rate. But in fact, that's going to go along with a weaker case for investment. You're going to get a lower optimal environmental investment ratio typically from this kind of a change in the setting. There are a number of other extensions that I've been thinking about. The basic model has this property that the optimal environmental investment ratio and hence the resulting probability of disaster, those are both constants in this model. Now, there are a number of features of the model that make that so, and there are a number of changes in the dynamic structure which can alter this result and mean that you might want to have, for example, a rising path of environmental investment. So Nordhaus, in his many works in this, tends to focus on that idea that there might be kind of a ramp-up property where you might not do a lot of environmental investment today, but you're going to be planning on doing much more in the future. And there are some dynamics and nonlinearities that can produce that kind of result. It doesn't come from the basic trade-off between now and later that's in the model that I have. So the model that I have has the property that if you do more environmental investment, you have less consumption today because you're putting more of your GDP into this mitigation activity. And you're going to get some flow of benefits more or less into the indefinite future, which in a simple framework shows up in terms of a lower disaster probability or lower sizes. So there is a dynamic there, but in the baseline model, the trade-off is the same if you think about it today or next week or next year. It always looks the same, and that's why the optimum is a constant investment ratio. So you can change the model in terms of a richer dynamic so that that trade-off does shift over time, and then you're going to get a whole path of environmental investment ratio as being optimal rather than a constant. I think that's probably more realistic. I don't think it changes the basic insights. In fact, I think it clouds the basic structure in terms of what the trade-off is, which I think is captured by the simpler model, but I'm certainly not averse to having that kind of extension of the model. The results that I have in this simple model certainly are consistent with the arguments from the Stern Review that you might want to invest 1% or more of GDP. It's very easy to get that kind of result here, but the reasoning is basically about fat tail events combined with substantial risk aversion. And that's not the key properties that are in the Stern Review that gives you 1% of GDP or more. But you can get an answer that's maybe even higher than what was being argued for in the review. In generating some kind of illustrative quantitative results, I appeal to some of the findings that I have from the work I've been doing on rare macro disasters. So that was particularly the case with regard to how averse people are to risk. That's central to the analysis. And I think that that application from the previous analysis works very cleanly. I also assume that the potential size distribution of disasters was the same as in the previous work. And that might be reasonable, but I think it's a less clear-cut way of using the previous results. Even with this way of using the kind of rare disaster analysis I did before, there are two key parameters that come into play in the framework I have, which are not informed by the history or by the previous applications. So that's this policy effectiveness parameter. How much do you get as a payoff by doing something? And it's something about the baseline environmental disaster probability, which I can't get from the data because I don't have any realizations. So in order to apply the framework, I have to think that there was this history back more than 100 years where we had no realizations, but somehow looking forward, the world is different, and the probability of disaster is non-trivial and is maybe 1% a year or 0.5% per year or something like that. But that's not coming from what I see in the history. So those two key parameters are things that I can show how the results depend on them, and I can take account of the fact that there's uncertainty about those things, but I can't really pin down those values more, and obviously the results are dependent on that. So that's where I stand basically in terms of this research at this point, and I'm happy to take any questions or harsh criticisms that you might want to raise.
Okay, thank you. Thank you very much. We do have... We do have 20 minutes or so for questions, so just raise your hand if you have a question.
You may have to ask one.
I've got one to ask you, actually. I'll ask you to give them time to think more. What would you say about the argument that many people make that the result of the environmental disaster is not a sudden big disaster, but it's a gradual deterioration of our environment and conditions. So you wouldn't see in the data. It might be, it might be a gradual melting of the ice, which little by little raises and covers more earth, or it might be something that makes forests disappear, trees dying little by little, but you wouldn't see there's a big fall in GDP. It's sort of gradual process that is not measured by GDP. And that's, for example, that's an argument that Al Gore has been making, that I heard a recent talk by him. That's more or less what he was saying.
That's the kind of extension in terms of dynamics that I think might be important in this setting. I think if you had the kind of dynamic structure that you're outlining, you could think about the overall consequence of getting on a path which has some kind of deteriorating effect, measured either in terms of GDP and consumption or in terms of some other form of amenities. And then you can think of sort of capitalizing that into something that I modeled in a simple way to think about a downward jump at a point in time. So I don't think necessarily it's going to change the nature of the calculation. It might change the dynamics in terms of the way you're going to choose your intervention, but it may or may not do that. It's also true in the macro applications that this way of modeling disasters was really a simplifying assumption. So when I applied this to the macro events, wars, depressions, etc., I initially thought about it as if the GDP fell instantly by 20 or 30% when an event occurred. So that also is unrealistic in several dimensions. Disasters don't occur within 2 seconds and have a downward jump. They tend to be elongated. On average, the downturns associated with these rare disasters were about 4 years, for example. It's also true that once there's a disaster in the macro application, it's not permanent, but there tends to be a recovery, particularly after wartime. Recovery is actually pretty strong. You tend to recover about half of what you lost during the disaster itself. So extensions to take that into account are of some significance, but they don't really change the basic trade-off idea and the basic information in terms of explaining things like the equity premium. So I think the environmental application is in some respects similar to that, but so I think a richer dynamics is important. Some of that might also have to do about learning what it is that you can actually do, how you can accommodate yourself to events that have occurred. I think there's a number of ways in the dynamics in which the dynamics can be enriched that I haven't put into this framework yet.
You have no excuse now. You had enough time to think about it.
I'm not sure this is my view, but I can imagine that some people think that at some point there's going to be satiation for things like consumption. And so if that's your utility function, then you may think quite differently about how much you want to invest in the environment.
Yeah, of course, the approach I've taken is standard in the sense of having something that looks like diminishing marginal utility, but not to the point of satiation. But I've done that within a setting, which I think is important, where you're distinguishing attitude toward risk from willingness to substitute over time. So you certainly have the idea in this framework that as you get richer and richer, you're sort of putting less and less on it. But how that trades off with the environmental part is also an issue. I mean, in the standard setting where you think about an environmental catastrophe as just reducing consumption and GDP, so the satiation isn't really changing the trade-off there. It's just that you have different ways of having less GDP, less consumption. So modeling it as two different types of goods, consumption, environmental amenities, depending on which way you model that in terms of functional forms, you could capture the idea that as you get richer, somehow you're putting more and more weight on the amenities and less weight on the ordinary consumption. That's not exactly the way I did it when I thought of them as being completely separate, but you could certainly incorporate that into the model.
Sorry about that.
It seems to me that maybe you'll get a suboptimal rate of investment, even with this analysis, because the rich countries will have a lower sort of covariance of their consumption with the environmental disaster, because they have the ability to repay citizens or invest in adaptation, whereas poor countries, which are more affected by environmental disasters and so have a higher covariance, won't have the capacity to invest in environmental benefits. I'm not sure if that's clear, but...
So I'm implicitly thinking about a one-country model or a global model, and I built in enough of this sort of proportionate effect kind of thing so that when everything doubles, it doesn't really change the optimum with regard to the share of GDP that you'd want to put forward for mitigating these risks. That doesn't have to be true, but it's a characteristic of the model as I developed it. So that means as the world gets richer, in the way I had the structure, you wouldn't change the share of GDP that you'd be devoting to this mitigation. The absolute amount, obviously, would be rising, but the share would not be changing. So if you think about poor countries versus rich countries in terms of the world being poor some time ago and being richer, then you wouldn't get that kind of effect. I mean, a different effect is that the world is really comprised of many countries, but the environmental problems might be mostly global. And then, of course, if you determine an optimal global amount of environmental mitigation, you have to think about how to share the expenses. And that has the usual kinds of problems with regard to sharing. I don't know if it's so much about poor versus rich, but there's certainly an incentive to free ride by both poor and rich in that kind of a model. So I'm not sure it's going to make the case that the rich should particularly be subsidizing the poor countries, but certainly it can be an issue in terms of coordinating on the optimal investment.
Okay, there was a question here. You need to pass the microphone.
Perhaps your model could allow it, or maybe not. But so one of the chief arguments of those in favor of doing something about climate change would be that the more we postpone it, the more serious the catastrophe will be, or the probability of a catastrophe is increasing over time. Would your model, would you be able to model this, or would it make a difference? Would it be important?
So as I think you know, I mean, that's not in the model as it stands, but another kind of dynamic extension could certainly allow for that in terms of, for example, having the probability and size distribution of disasters depend on some accumulation of past GDP or past emissions, and then particularly if it does that in some kind of nonlinear manner, you could certainly get that you would have this potential for a rising disaster probability. So in that extension, as I would think about it, you would understand that at the beginning. So your optimal investment path would take account of the fact that if you delay, you'd be getting into this problem. But that doesn't mean you'd have a constant environmental investment ratio being optimal in that setting. Probably won't be optimal to be constant. But you'd certainly take account of the fact that the thing will be rising if you don't do anything about it. And if there's some irreversibility, that might make that even more consequential. If you go beyond some point, you can't reverse it. But in the way I would think about that, you would understand that also beforehand, so there'd be a very strong incentive to avoid going too far. So I think an extension of this model could incorporate those features, but as you suggest, it's not in the model as it stands.
More questions? Yeah, this one upstairs. You might have to shout. I know there is a microphone. It's coming to you.
I'm very interested in your model, how your model can be used to explain equity premium puzzle. Can you explain it in more detail? how your model may be related to equity premium puzzle.
You know, the history there is that Mirror and Prescott had their paper in 1985, arguing that if you calibrated the model with the uncertainty that you saw by looking at fluctuations in annual consumption and GDP, particularly for the US, and combine that with a kind of reasonable rate of risk aversion, that you didn't get enough, and you couldn't get anywhere close to explaining the equity premium puzzle. 3 years later, Tom Reitz, in his PhD thesis at Iowa, wrote a paper saying that basically I can explain the equity premium puzzle, and he raised this idea of these rare macro disaster events. But at the time, he was only thinking from a US perspective, and the only disaster he had to consider was the Great Depression of the 1930s. But he tried to argue that the potential for these big events, the US Depression, you had a decline by about 25% in GDP, for example. He argued that with enough of a probability on that, you could get something big enough to explain the equity premium without crazy risk aversion. Now, I didn't know anything about that research contemporaneously, and my research historically hasn't been in finance or asset pricing. So I only started thinking about these issues around 2006 when I somehow started on this topic. And I thought that this kind of rare disaster perspective might work, and then I was motivated to look into what the history of thought was on this subject. And I consulted John Campbell's survey article on asset pricing, and that was how I found the Reitz comment on Mirror and Prescott. It's back in the late 1980s. Now, as I reconstructed this history after the fact, it seems like Mirror and Prescott persuaded the profession that the rare disaster idea was not going to work. They had a comment on Reitz in the same issue. This is all in the Journal of Monetary Economics, basically saying that this is a stupid idea and it's not going to work quantitatively. So my reconstruction after the fact, since I was not at all involved with this, was that they had persuaded the profession that this was not a fruitful line of research. So there was a little bit of work on that, but basically there wasn't much after that. So not coming from the finance area, I hadn't been persuaded that this was a useless line of research. I thought it was worth pursuing it. But then I didn't just look at the US, I looked at the data for as many countries where you could get the long-term data, which turns out to be now around 40 countries. And because you get events that are substantial in size, a distribution that goes out to, say, 40, 50% of GDP declines, then it turns out that with risk aversion on the order of 3 to 4, that's kind of big enough to give you the required return on equity being substantially above the risk-free rate. That seems to work more or less quantitatively, you know, subject to a lot of potential criticisms and details. So that's what Ursu and I, for example, claim to have shown in several papers that were on this topic. But I think the original idea here goes back to this paper by Tom Reitz. So after I did this work and I wrote some op-ed about it and I said that the idea came from Tom Reitz, he wrote me and he said, well, his mother was very pleased that I had mentioned him in this op-ed. And would I come to the University of Iowa where he was and give a seminar on this research? And so I did that, but I found that Tom had stopped thinking about these topics many years ago, and he really didn't have any new insights on it. I was disappointed. And mostly at the University of Iowa, he runs this Iowa betting market, which is particularly related to elections. So they have a betting market from which you can infer probabilities of various outcomes, electoral outcomes. So that's what he was working on. And, again, part of my reconstruction is that I think Mirror and Prescott pushed him out of this area and into doing some different work. So I thought that was too bad. So that's what I know about this history of thought.
Very good. Yeah, I will take, I think, you very fast.
I was wondering if you had any recommendations or suggestions for what governments or policymakers need to do based on your modeling. Thanks.
You know, I've feel like I understand this problem much better than when I started thinking about this research, and in terms of the basic trade-offs and what things matter for the answers. I don't feel that the particular quantitative numbers that I've gotten so far are so much of an accurate guide to how much globally ought to be invested in this problem. I think I have a little bit of an idea now about the right ballpark and what it depends on. I mean, it might be fundamentally that there's just too much uncertainty in this area, and you're never going to be able to pin it down, but nevertheless, you're going to have to make decisions. And that's a difficult problem, but I guess you're going to have to do something. And, so the parameters that matter a lot that I didn't know how to pin down, I've been trying to think about how to get more information on that. For example, one of the problems is you don't see these environmental disasters. You don't even see things like hurricanes and tsunamis being big enough. You do have a whole list of disaster events of that type. They're just too small to show up in the data as being consequential, like being 10% or more of GDP. So one thing I thought, well, you can look at the distribution of all these smaller events, and I thought maybe you can extrapolate from that to thinking about what the size distribution looks like in the bigger range where you don't see any observations. But so far, my attempts to do that seem to be a failure. I don't know if you can really do that. I thought maybe that would be feasible.
Yeah, we'll take two more questions of the two people that expressed their interest on here and one there.
Do you think that we could use your model to determine how much sanction to put to Russia? We know that sanction will cost the West GDP, but it should
How much what
reduce
should go to Russia?
sanctions. It's going to cost the West, but it should reduce disaster events.
This is funny because I wrote an op-ed that came out on Tuesday about secession. And I'm not normally a fan of Putin. I think that the right to secession is something that ought to be probably a fundamental liberty that should be in constitutions. Particularly if you think about states sort of voluntarily coming together, like the U.S. states, and how is it you can come together but you can never leave without a war or something like that? Now, of course, Putin is very selective. He thinks that Crimea should have a referendum, but he doesn't think that Chechnya or Kosovo should have those things. So I'm not really defending Putin in general, but I think it was actually quite reasonable what he's done so far in the Crimea. I wouldn't do anything in terms of intervening or sanctioning there. I hate to be on his side on something, but you know, you do enough things, eventually you get to one that's correct. But in this op-ed, I talk about some history about the right to secession, particularly from a U.S. perspective. The U.S. Constitution is actually completely ambiguous about whether states can secede, even though we fought the Civil War mostly over that issue. And we decided from a military point of view that you couldn't secede, but that's not some fundamental right or something. And I found some marvelous quote from Alexander Hamilton about why secession rights were really bad. Hamilton was mostly interested in strengthening the central government at the time of the Constitution, so he thought secession would really limit the power of the central authority. And I think that that's true, but if you move away from the 1780s to today, I think the problem is not limiting the power of the central government. I think it's the opposite. So I think if Hamilton were around today, he would have a different perspective, and he and Putin and I could get together for a beer.
I guess by calling Putin selective, you mean that the West has been uniformly applying democratic principles in these matters of secession and civil wars.
Well, we're completely inconsistent on whether when we argue that this kind of referendum or secession is satisfactory and when it isn't. We don't have a general principle either. I don't know if most people realize that Ukraine became independent by declaring secession from the Soviet Union. And secession was actually legal under the Soviet Constitution, which is very unusual. Most constitutions don't say that. But the Soviet Constitution actually did say that you could secede as a Soviet republic. And that was the legal basis by which Ukraine became independent. So it's a little ironic now that they think that other parts of the Ukraine can't have a similar kind of
Okay, there was one last question here, please.
Hi, have you considered a multinational model with the idea that a lot of past natural disasters have been local enough that a country could borrow to help recover from them, versus if climate change really comes to the worst predictions, it'll affect the globe and there won't be that capacity to borrow to help mitigate those losses and help recover quicker?
Yeah, I think if you think about the environmental catastrophes that matter, they must be basically global, and that element would be then central. You could certainly think of other kinds of environmental events that have more of a local character. You know, like air pollution in Los Angeles, I think, was kind of a local problem. So those problems are perfectly interesting, but they're not going to be the kind of disaster risk that's relevant in the framework I was considering. So I think the global perspective is more important in terms of the disaster perspective that I was trying to take. If you thought about the disasters as local, and then you take the fact that, you know, I had 5,000 annual observations on the underlying national accounts data, but I didn't see any of these disaster events of an environmental type. If you had 5,000 independent events with 0 realizations, the probability per year of such an event can't be very high if you see 0 in the sample. If you think about global events as what really matters, then you basically have 140 years or something. And then it might be possible that you can have a significant probability of an event and not see any realizations in 140 observations. That's more conceivable. But again, those are the kinds of events that are, I think, more pertinent as the global ones. That does bring in this issue again about the coordination among sovereign countries in terms of how you're going to share the burden of doing something, given that the spillovers are central there.
Okay, thank you. Well, it remains for me to thank Robert for a big lecture that we get with small probability here.